it's definitely been fun in some ways and frustrating in others. It was a little bit challenging. I mean, I started working with Andy Warfield at the beginning of 2017, and then I officially started the PhD in the fall, and then 3 weeks into the term, he quit, and he went to Amazon. And he's still at Amazon, actually. I asked him to give a guest lecture, so he's going to do that. He just gave a lecture. He gave a talk last week at a conference down in Silicon Valley. It's big in the storage arena because that's where he works, and I suspect he might use something along those lines. Some of the reason that I put the lecture in for Thursday, which is about formal verification, was because of some of the work that his team at Amazon have done, where they've actually used formal verification methods in building distributed systems. And I've played around with those tools, but I haven't used them enough to really be adept at them. But that doesn't mean I shouldn't be telling you about them, because I think that, especially if you're getting into distributed systems at this point, it's a really good idea to be looking at using tools that allow you to validate your designs, validate your models before you go off and build them. And if you've listened to what I've been saying about like the projects, I keep saying that. Plan what you're going to do. Don't sit down and think you're just going to be able to whack this off by typing on a keyboard. Often, a lot of these problems are easier to solve when you're away from the keyboard, because now you have to think about it. Now you have to build an actual model of it and decide how you're going to test that model. All right, so it is time to go. I will get started here. This is going to be very short. Logistics was a lot longer before. I don't think they're quite done grading the reports on Project 3. I have to go. Well, they may be done and I didn't notice yet. But the last time I checked, there was still some to do. So I'll check and make sure. And if not, I'll try to find. I'll just sleep less and get it done. Nothing else has really changed there. Just to note that we're now 2 weeks out from the due date on Project 4. I don't know if anybody has started it. I've seen some things, some conversations at least on Discord. So I know a couple people are at least thinking about it and struggling a little bit with it. I did put a post up in Piazza yesterday, which is a link to several hundred slides from the DS Labs, Ellis Michaels. DS Labs folks down there at the University of Washington. And there's a lot of good information in that. I'm assuming there are no problems actually getting home. My plan is still to do Zoom office hours at 1. If you have questions, you can post them if you don't want to appear. I actually did office hours on the Tuesday 2 weeks ago, but forgot to record them, which was kind of dumb because I was talking about Project 4. So I'll do it again. I'll talk through Project 4 today because it'll be more topical. Blah, blah, blah. Let's see. I don't actually have any required readings this week. Again, lots are recommended, which I know means people won't read them, but maybe someday you'll actually go back and go, wait, there's all those interesting things, and maybe I should go look at them up. So these are about the distributed consensus algorithms we've been talking about. And which one is best? Now, here's the interesting thing that's becoming very obvious to me. I've never really stood them up next to each other and gone through them with a fine-tooth comb. They're all basically the same. There are small differences in the things that they do, but there are very large commonalities. They all rely on consensus, on quorum consensus. Remember when we were walking through view stamped replication, and at the end, we had our primary fail, but we were able to reason about the fact that we had a read quorum and a write quorum. And what was interesting about that was we didn't actually have a read quorum and a write quorum now. We had a read quorum and a write quorum when the decision was made, and we could reason about it. I'd never really thought about it that way, and I said, wow, that's really cool. I liked the way that came out. So the emphasis here today is going to be on Raft, but I'm largely going to end up talking about how it relates to the other algorithms. I mean, somebody was asking about, so there are these 3 papers about Paxos, and each of them uses different terminology. And people are trying to equate the terminology across these papers, and I'm realizing this is just a mess. It's like somebody sat down and said, let's re-explain this thing and just use completely different terms. Because when you look at the original Paxos paper, it doesn't separate out the proposers from the database, right? You've got priests with ledgers, and they have things they write in the front of the ledger and things they note in the back of the ledger. Okay, so they keep track of the ballots in the back of the ledger, and they keep track of the decisions in the front of the ledger, and it's like, fine. But then you start talking about replicas, and what are replicas? Well, the reason that PMMC switches to this terminology replica is because it became in vogue. Gosh, 15 years later, people are using slightly different terms for things. This will happen throughout your career. You will probably not think about it. Maybe someday, 20 years from now, you'll go, yeah, the fat guy that taught distributed systems, he was right. We do just like randomly change the meanings of words. I have seen this where you start with a term. One of my favorites, because I used to teach about it all the time, was this thing called fast I/O, which originally was introduced as a performance optimization for an I/O path. But over the years, it got used for other things, and then they found that the fast I/O path itself, the things that were there for making I/O fast, didn't do anything, so they removed them. So by the time you were done, you had this thing called fast I/O that had nothing to do with I/O. And that happens incrementally. And it's not the first time I've seen it, and it's not the last time that I, or probably you, will see it. So always be aware. Yes, it's reasonable to start and say, okay, I think I understand what that is. But then when you start trying to equate it to other systems, you're going to find that yes, there is a leap there. That's why I prefer to look at what the model is, because the terminology can sometimes obscure the model. Anybody have any questions? I mean, there's 4 of you who made it today. See, I could have brought 1 dozen donuts and still had plenty. I wasn't bringing donuts on the bus today in the snow. All right. I'm going to go a little bit different direction today's failure, because this is actually drawn from my own personal experience. And the reason I picked this is because it emphasizes an important point that people have been struggling with in the projects, and that is efficiency. So the way that we short-circuited FLP was to say we are not going to allow unbounded message delay. The problem with that is it creates a different class of failures. So in this particular project, what we were hired to do was to take an existing system that was working on top of a fabric, a network fabric. So you can put storage devices on these network fabrics, and all the computers attached to the network fabric can talk to all of the storage devices. And this is used in certain kinds of high-performance computing. The Intel InfiniBand is very popular in HPC right now, and it's basically the thing that replaced what we were using at the time, which was called fiber channel. These are very expensive because they really do create essentially direct connections between everything on the network, or mostly direct connections, because it's not quite cost-effective to make everything connected to everything else. What we do instead is we have these things called crossbar switches and whatnot that make it all really fast. Fine. So what that meant was I could have multiple computers sharing access to the same disk drive. Well, doesn't this sound like just a disaster waiting for a place to happen? And so what they wanted to do was to take an existing solution, which was SMB, the server message block protocol that runs on Windows and Linux and whatnot, that does file sharing. And they wanted to short-circuit the I/O path. Gee, we're back to fast I/O, aren't we? We wanted to short-circuit the I/O path by allowing the client computers to read and write directly to the area on the disk where the data was. But we'd still use the file server to control the metadata. So anything that changed the shape of the file, if we extended the size of the file or we truncated the size of the file, we had to go to the file server. But once the file server had allocated space to it, any of those clients could directly read or write. This gives us a really nice form of parallelism. It's very efficient. And if you actually look at parallel distributed file systems like Lustre and Gluster, and there's a bunch of others, but Lustre is the original one, and it's still very heavily in use. And I know the guy who wrote it, blah, blah, blah. They actually do pretty much the same thing, which is you have metadata servers that control the placement of the data, and then you have data servers, and you can parallelize your I/O across those data servers and not have to interact through the metadata servers. This is a common thing we do in systems in general now, which is we separate out what we call the control plane from the data plane. And we make the data plane really fast, and we make the control plane more complex. Because we're trying to isolate the complexity because that slows us down. So we only go to that layer when we need it. Well, this is a weird way of implementing it. I admit it. But it was actually pretty interesting, and we did make it work. And the company we did it for ended up being purchased by Hewlett-Packard because of this work that we did, and HP then proceeded to stop using it. If you're working in tech and you work for a small company and it gets acquired by a big company, you should pretty much expect that the big company is going to come in there and do all sorts of things that you look at and you go, why are you doing this? This is why you bought the company. Yeah, but we had a couple $1 billion lying around that we didn't know what to do with, so we decided to spend it this way. So here was the interesting thing. So we build all of this stuff around the existing pieces to make them make their behavior change. We had a server and we had clients. So when we wanted to grow the size of the file, what we'd have to actually do is ask the server to grow the size of the file and allocate the space for it. And we knew how to do that. We knew how to make it do that. But the problem was, underneath this was an NTFS file system that the server would talk to say, please allocate the space on this disk that happens to be on this fiber channel network, and it would do that, and it would insist on zeroing out all of the data blocks. Got to protect your security on a shared access open network. Right, okay. So we have a component that was built with a very specific model. Have to protect the data on the disk, can't expose it to other applications, that wouldn't be safe. But we're using it in an environment where that's not actually an important constraint. So what we're trying to do is we're doing a very classic kind of computer science trick. Well, I would say software engineering trick. We lie. We tell the component what it wants to hear. But NTFS snuck in there and it was zeroing this stuff out. And what we found was that if we extended the size of the file more than about a gigabyte, I think it was a gigabyte at the time, this was 20 plus years ago, it would take more than 10 minutes to zero out all of those blocks on this drive. And the original request from the client would time out. So how do we get around this? We actually got around it by building yet another component underneath that would detect when NTFS was zeroing out those blocks in the file and say, yep, we did it. That's the why part. Yeah, we did what you asked. No problems. Life's good. And we didn't time out anymore. But this idea around timeout ties back into this whole idea of how are we going to circumvent the FLP problem, and that is we're going to bound the amount of time we're willing to wait for anything to happen. And so that's the failure example that I'm using today. When you fix something in one way, like putting a time bound on that, you can potentially still create other problems that will cause you to time out anyway. Now you hit your timeout because you've introduced this new potential failure. We're only willing to wait so long. This is very common. I almost replaced this failure today because I don't know if anybody, slides, blah, blah, blah. If anybody's ever heard of a company called Dish Networks. They're a satellite broadcast company that transmits TV signals to people. Their website, in fact, basically all of their infrastructure has been down for like 2 weeks now? Yeah. I think they still can transmit, but basically, the theory is that they were hit by a ransomware attack. And then there was the LastPass debacle. Anybody know about LastPass? Well, they just announced, or they just revealed that in fact what actually happened was that one of the key developers in the company had their own computer hacked, and they had their passwords for their corporate system on their own home computer. Yes, exactly. In the back. What the heck were they thinking? Exactly. So that's the other thing. We build these really robust distributed systems, and there are failures that we never expect. How they couldn't have expected that, completely separate. Why anybody would actually allow that in governments. And that's ultimately the other thing that I keep hammering on is I talked about failure, and I always talk about failure, and remember that failure isn't always recoverable. It's great for us to build resilient systems, but building resilient systems isn't ever going to be foolproof. I know, it's kind of dumb to put the Vogon blowing up the Earth thing in there, but the point was there's always failures you cannot actually handle, and you shouldn't handle them. The best thing in that case, like the ransomware case, is to say, well, you better go get your backups out because things are kind of screwed up. It's fun reading sysadmin discussions because they end up seeing a lot of the failures. They're the people who get called in to fix things when they break. And so, for example, they talk about Microsoft's cloud services for email and how Microsoft doesn't actually back up your data. If you want backups of your data, you have to provide it separately. The same thing happens with virtual machines. There's a product called Veeam that's very heavily used with VMware virtual machines. And it backs up the virtual machine images so that you can recover them. That's part of disaster recovery and not the kind of failure management that we do in distributed systems. It's still important. But always remember, there's a disaster recovery team that better be doing their job so when you can't fix the problem, somebody else can. So we're going to be talking about Raft today. But like I said, it's going to end up being more of a comparison of Raft and Paxos. So I'm going to start with a review of Paxos because it's been a little while since we talked about this, and I'm sure you've all forgotten everything over the reading break. I hope so. I mean, wasn't that the idea? So people struggle with Paxos because it's hard to wrap your head around. And Lamport wrote this very whimsical paper, the whole part-time parliament paper, and when you sit down and you actually start reading it, I'm sitting here reading it because you guys are asking questions about it, and I'm forcing me to like hold these three papers up next to each other going, yeah, I can see why this is a little confusing. Versus, reading this weird paper 20 plus years ago, and then this other weird paper 17 plus years ago, and this other paper 10 plus years ago. You don't necessarily draw the inferences there. So our challenges are figuring out how Paxos works, why it works, and how do we actually build real systems with it. Well, so we're kind of in Project 4, we're kind of in the how does it work and why does it work phase. And then in Project 5 is where we're building a distributed key value store. And that's how do we build a real system with it. So we are definitely going through these things. So the big challenge here, or there are a couple of big challenges. One of the big challenges is partition, where we end up with a split brain. That's why we ended up using a quorum consensus model. And I talked about crumbling walls because it is a generalization of quorum consensus. I spent most of my talking about Gifford's quorum consensus model because that's the quorum consensus we most often use, which is a reader-writer quorum consensus mechanism. Crumbling walls said, we don't really need to have a strict quorum, like a numerical strict quorum. We can actually organize our data in ways that is a little more clever about this. And that's what I thought was kind of cool about it. So we can have cases where the primaries and backups can't communicate but the clients can communicate with some or all of those primaries or backups. That's the interesting partitioning case. I don't really care. If a client gets partitioned off from the network, sorry, plug your network cable back in, reboot your network, stop using UBC Secure and use EduRoam because we know that works better, even though it's all the same hardware. How do you handle these failures? Well, you can have a backup that tries to self-promote, but as we've actually talked about, that doesn't necessarily work super well. Why did we introduce the view server in Project 3? Because if we only had a primary and a backup, and they partitioned, they have no way of knowing if it's a partition between the two of them or if one of them died. So our risk of having a backup self-promote is that it means that the primary might not be dead, in which case now we end up with 2 copies of our database and they're no longer consistent. I hate when that happens. You ever had a file you kept on here and then you edited it there and then you couldn't remember which one was which and then you're using cloud storage and it just marks them as conflicted? Yeah, I know how it feels. So this is the consistency side of it. This is back to CAP. Consistency, availability, partitionability, partition resistance, that's the exact word. So this is the partition problem. We are now worried about the consistency problem. Paxos and view stamp replication and Raft and quorum consensus are all about consistency. They want strong consistency. We're going to find ways of relaxing that so we can get eventual consistency, which is a weak consistency, like S3 actually uses, and I've talked about that. So a common approach to this, because of the environment we work in, is to model everything as a state machine. That's what the framework does. Those messages are, in fact, the inputs to our state machine. They are the transitions from one state to another based upon the message that we receive. What we are really trying to do is to get identical state machines running on multiple computers, and we want them to come up with the same result, even if the messages are delivered out of order. I mean, if they're always delivered in exactly the same order, no problem. That's why we do log replication, because if we have a log, we have a canonical order of the operations, and thus it's easy for us to replay that into a state machine. The hard part is, since we can reorder messages on the network, there's no guarantee that the messages are arriving in the same order, whether we do that in a replicated log or we do that directly with a protocol like Paxos. So in this scenario, now I'm going to start using that term replica that we see in PMMC. In this scenario, we have 3 replicas. We don't have a primary. We don't have a view server. This isn't Project 3 anymore. This is Paxos or Raft or view stamp replication or even quorum consensus. The replicas each have a log of the operations that they have processed, that they have seen. Clients send their requests to a subset of the replicas. Now that is not a strict subset, so it could be all of them. That's the we're going to broadcast it to everybody approach. What's the problem with broadcasting it to everybody? What are they going to do with it? Because remember, if I'm one of those replicas, this is Paxos now, right? If I receive a request from a client to perform an operation, I create a ballot. I propose a change to our replicated state machine. So now I broadcast that and I say, okay, all of you jump in now, all at the same time, and propose a change. Does this sound like a good idea? I mean, we talked about the back-off approach where when we lose ballots, you delay the amount of time before you do your next proposal in order to break that tie. But the downside to using broadcast is that now you've created this massive collision. Like everybody jumps on the network and tries to send their packets at the same time. If you've never studied Ethernet, this is exactly what Ethernet does. You look at you literally look at the connection. This is traditional Ethernet. You look at the connection, you say, do I see a signal going across that? No, I'm going to start transmitting. And I know that I have a period of time where I might collide. Collision detection, multiple access. You do it in cell phones too. As the frequency of the messages goes up, the viability of using a broadcast model goes down, because now no one can hear because everyone is shouting all of the time. So that's why I said subset. And make it a broadcast, but from an implementation perspective, what probably makes more sense is for you to say, I'm just going to pick one and send a message there, and then if it times out, I'll send it someplace else. Because in the common case, and when you optimize for the common case, because you're optimizing for performance of the overall system, not for the failure case. So when you optimize, you say, I'm going to do it that way. I'm going to do this fallback model. And occasionally, like maybe, I don't know, once a day or less frequently, yeah, the one you picked, you got unlucky. And you time out. Maybe you could be really clever about this and start keeping track of who's responding more quickly, and you could pick things based on some sort of historical data that says, well, this is the best node to pick, because that's kind of how you try to get load balancing. The reason we do load balancing is precisely to avoid that whole collision problem. And what I've just described to you is basically a really rudimentary load balancing mechanism. You could do it round robin, you could do it random pick, you could do it based on how fast it took to get the last response. Doesn't matter, makes no difference. Client sends a request for the subset of replicas based on the client's own decision process. Now the replica that received the request from the client has to propose the change. Looks like the picture is clipping the slide. That should be consensus, not consents. Consensus then requires that we commit that operation in our log and return the result to the client. So the client gets the response once the replicas know that this operation has committed. This is all back to two-phase commit. We took two-phase commit, which was basically we have a coordinator. That's just a different term for leader. Then we generalize two-phase commit into three-phase commit by saying, okay, well, instead of making the messages synchronous, we can allow them to be asynchronous. It wasn't a big jump. It's the same exact thing. It's just now you don't wait for the response in the messages. That does make it a little more complicated to reason about, but that's effectively what's happened here. And now we add this distributed consensus on top of that, but it's basically under the covers still two-phase commit. We have to get somebody to make a decision. The proposer in this case is the coordinator. The proposer says here, and they gather the votes. We actually are a little bit better off than we were with two-phase commit, because we're no longer requiring everyone vote for it. Because what we're doing is replicating state. So we can rely on our replication to say, we don't have to have 100% of everybody voting for things. We just need to have enough that we know that there's only one agreed upon outcome, hence the quorum. So there's this idea of a leader, but we don't have to have a leader. And if you actually look at the original Paxos, one can argue that there is no distinguished leader. Any priest can propose a ballot. But once that priest proposes a ballot, they are effectively the leader for that ballot. So it's not quite leaderless, it's like micro-leadership or something. You get to be leader for this ballot. But other people can step up and say, I want to be leader too. In the original Paxos paper, we used the terminology proposer, acceptor, and learner. It never uses the term leader. The way we got parallelism here was to say, well, we can just simply run a Paxos instance for each thing we're trying to decide. And that's kind of the extreme sharding example. So every value in your database gets a different Paxos implementation. Probably overkill, isn't it? That's why when we look at Project 5, where we're going to be doing sharding, we are in essence breaking up the state machine. We're breaking up the database into distinct pieces. And we can run different changes across those different shards. We're trying to reach that balance between everything is sharded and nothing is sharded. Because remember, in Project 3, we essentially had one shard, which was the entire database. When a backup came up, you had to replicate your database to the backup. So it's not too hard now to say, okay, great, well, I could basically split that up and have parts of the database replicated in that fashion. In Project 3, it didn't make any sense, but in Project 4, it makes a lot more sense to start thinking of it that way. And in Project 5, that's actually the whole point. That's how we build useful distributed systems here. So that led to multi-Paxos, which is described in the original paper, and that was where we have a leader election. So now our decision is to implement a Paxos implementation to decide a leader. So we vote on the leader. And that happens in ViewStamp replication, it happens in Paxos, it happens in Raft. Our failure protocol is to elect a new leader. And anybody can ask for an election. Then once we have a leader, now it looks a lot more like two-phase commit, because the leader is basically the one who contacts the other parties who are involved in this and then makes the ultimate decision and records that in their ledger, in their log. Multi-Paxos is actually the more popular of these to implement. Question in the back. Yep. So someone starts a new election and either, okay, so you said this was a partition. You can't, in which case you try to elect a new leader. But remember, to elect a new leader, you still have to have a quorum. So in order to get that quorum, you have to be in the majority. You can never, so that's the whole point of the quorum, is just to make sure you can never have two leaders. You can never have that split brain. I mean, it's a lot easier when you're thinking about that as a group of 3 versus a group of 37, but it's exactly the same problem. Multi-Paxos is a more popular implementation model than original Paxos. Project 4 is actually original Paxos. So it's the simpler version, and then multi-Paxos is a generalization of that. In ViewStamp replication, it is, for all intents and purposes, multi-Paxos, as is Raft. Because there is a leader, and there's a leader election protocol. So each replica maintains its own operations log. Clients can send a request to any of the replicas or all of them if it wants. The replica initiates the proposal. It uses its latest sequence number. This is interesting because a couple of people have said, well, I replaced the string with something else. And if you actually look at the original part-time Parliament paper, in fact, the way that he constructs the ballot numbers, so he has to split the space up, is that he makes it a tuple of the priest number and their ballot number. And essentially, the algorithm I gave you is a mapping of such a tuple onto integers. The Lamport approach will be flexible, whereas mine wasn't, because mine would be only for a fixed size. The Lamport approach is flexible because it would allow you to add participants, and that will be important. So that might be why you'd want to use a string. view stamp replication and Raft both use IP addresses, the network address, as the way of selecting a leader. So in the example that you gave above, where you have a partition, you don't fight too much over the leadership because it's based on a property that is inherent in the individual node, i.e. their network address. And that's really easy for everybody to look at and to decide. So that particular kind of election protocol makes it super easy and super fast to converge on a new leader. Whereas if we really actually did this through a whole balloting and randomization process and everybody saying, I want to be the leader, you can see how that would take longer to converge. It's not wrong, and there may very well be times you find a case where you don't have a single network address, or you don't trust your network address, or something like that. So you'll come up with a different mechanism for voting and deciding who's the new leader. Replicas initiate a proposal using its sequence number and its replica number. The proposers then collect the votes. Once a proposer has been told by enough other nodes that they have voted for that proposal, the proposal is now adopted. That replica notes in its log that this transaction, this ballot, has committed. And then it tells everybody, we all voted for this. Now, notice there's a trust model here, right? Right up front, all of these say we are not handling the Byzantine case. We will talk about the Byzantine case because it adds another wrinkle there. But when we start out, we just assume that everybody is honest and everyone is working in the best interests of the system. So in a practical implementation, we don't really separate out proposer and listener and acceptor. In a practical implementation, they're all the same thing. And I was trying to think of a scenario in which I'd want to have a split between the proposers, acceptors, and sorry, learners. I think I said listeners and learners. And they mostly would be large. The reason I might split things up like this is because I need something that's geo-distributed. That's when I'm going to start worrying about, essentially, the learner becomes like a caching layer. Because we don't have to wait till the learners know what the actual truth is. The acceptors are the ones that matter. The acceptors are the ones who have to know what the actual state of the database is, because in the simple Paxos paper, that acceptor is the replica. It is the owner of the database. And the proposer actually doesn't control the database. The proposer just simply controls the balloting process. So maybe you want to have more replicas of the database than you want to have proposers of the database. And that reminds me sort of crumbling walls, where we essentially have, we have to have all of the copies in one of the rows except the proposal, and one of the copies in each of the columns that are present in the rows except the proposal. And the idea is that we're minimizing the number of replicas, but we could do the same thing with proposers. I don't need to have 5 proposers if I have a large enough network. I don't need 5 proposers for every single row in my grid. I'm not sure that worked very well. It's about scale. That was what I come to, is I'm like, yeah, by the time I'm building something like that, I'm going to be working on a team of with a team of people, and we're going to be arguing on whiteboards, and we're going to be modeling this, because it's way too difficult to easily think about, why would I need to do this? And it's probably not until you see the problem that you're going to go, aha, I need to do this because it will help my scaling. So in Paxos, how do we reach agreement? You know, we pick a couple of clients. I picked client 42 because we know that's the answer. So we do a send put of 42 to server 1. Client 13 says send 13 and put that in X to server 3. We can't accept both values. That's the whole point of having this protocol. The reason that we use a quorum is to protect ourselves against a partition. We don't want to have that split brain. Pretty straightforward. Why does quorum matter? Well, Paxos was predicated upon the idea that we could accept up to F failures. So in the Paxos model, we need at least a quorum. So we need 2 times the number of failures we're willing to tolerate plus 1. So that's why I said that 3 was kind of the magic number, and it's always an odd number. And if you look at it and think of it this way, that's why it's always an odd number, because if I want to handle 2 failures, I need 5. If I want to handle 3 failures, I need 7, yada, yada, yada. So if we have n replicas and F is the number of failures that we're willing to tolerate, then we need to have the number that's left over, n minus F minus the number of failures, still be more than 1. The whole reason to justify this formula. So in that case, that means that n has to be greater than 2F plus 1. That's about as sophisticated math as we're going to have today. Raft. So Raft is an explicit leader election protocol. Once we have a leader, then we have a replicated log protocol. We have followers, candidates, and leaders in Raft. A follower can say, hey, I think the leader's dead. And then say, I'll propose myself as a candidate, or I'll propose you as a candidate. I don't think I've ever actually seen an implementation that proposes a different node, but there's nothing that prohibits it. It's like, I'm going to volunteer you to be the next president of the university, but you don't want to. I mean, you could end up in Michigan. So, of course, the candidate then has to ask people to vote for it. Either it gets the majority of the votes, in which case the candidate says, haha, I am now the leader. This is just Paxos, right? Our candidate's a priest. Sends out a proposal, says, vote for me. People vote for him, and he says, I got enough votes. Isn't that the Russian system? That's Byzantine, though. Not go there. And so there's all these little things that can happen because, of course, we have to have some mechanism for making our balloting decision. And our balloting decision here isn't based upon the policy. It's not like a political election, in all fairness. It's going to be based on something like, you have a higher IP address than I do, so I'm gonna vote for you. You have a higher IP address than him, so I'm gonna vote for you. It's based on something that we can easily all see, and most importantly, we can all decide the same way. Remember, that's the replicated state machine model. We all have to have exactly the same decision process. And I've used the, everybody trying to agree about what to have for dinner example, but in fact, the problem there is that we don't have replicated state machines because we are not replicated state machines. We're unreplicated state machines, so the problem is way harder. Once we have a leader, then any new proposals come from the leader, and that puts us into our log replication phase, which is we send proposals out, we gather up the votes on the log replication, and then we record the outcome of it. The only time we have a leader election is when that breaks down because the leader stops responding. Just like Project 3, where the view server is kind of the follower in that example. We don't have that elaborate election protocol. We just simply said by fiat, this is the way it's going to work. Here, we're trying to take, so I know I mentioned this, that one of the weaknesses in Project 3 was we had this single point of failure, which was the view server. So introducing the election protocol helps us eliminate that single point of failure. I mean, I hand waved it away when we were doing it. Yeah, I know. Pay no attention to the really big glaring, why are you doing this? But now we have to deal with it. So instead of having a view server, we now have an election protocol. Essentially, it is the same thing, though. We know who the primary is. That's our leader. And the reason that we have Raft is because they did a really good job of explaining the leader election protocol. I mean, for all intents and purposes, the reason that Raft became very popular, the reason that Raft was published was because their evaluation was it was easier for students to understand Raft than it was for them to understand Paxos, which was a weird thing for a systems paper, which usually focuses on the performance of the actual implementation, not on the ease of understanding. Especially as you dig into it and you begin to realize they're all the same. View stamp replication, Paxos, and Raft are all really similar. They're small variations, but usually they're covered by one of the other, oh yeah, and by the way, you could do it this cases for the others. So use the one that you can most easily wrap your head around. To walk through it in a little more detail. So a follower calls an election, generally because the follower thinks the leader is dead. That would be the best reason to call for it. The leader declares a term number, because that's like a ballot number, right? We have to have some way of saying, oh, by the way, this is, because we're not going to vote on old messages that show up. So this is going to get us out of the arbitrary reordering of messages on the network problem. And we have an index in the log. This is I know that everyone has committed the log, or the system has committed the log up to this point. And gosh, doesn't this just look an awful lot like a view proposal? I mean, as I was writing this stuff out, I'm going, this is pretty much what we did in view stamp replication, isn't it? And then all the nodes vote, and these are the acceptors. And once we have enough votes to know that a quorum has been achieved, now we have a new leader. Pretty straightforward. Yeah, there's lots of little loop-de-loos because things can go wrong because maybe nobody gets enough votes, or maybe we have a partition, in which case then there's going to be a bunch of machines in the partitioned off network that are never going to be able to elect a leader, which is kind of what we want. Now this goes to the A in CAP. Availability. This is the aliveness aspect. So is this system alive? Well, the partition, if you're in the minority partition, sorry, you lose. This is strictly going to allow the majority to continue forward. If you have a more complex partition, let's say the network is partitioned into 3 chunks, you can easily end up in a situation where no one can make any forward progress. That's because all these protocols focus on strong consistency. We would rather stop and have you call a systems administrator to fix the network than end up with the split brain, different versions of the database. So we have a bunch of rules for an election in Raft. There's at most 1 leader per term. Okay, well that kind of makes sense, doesn't it? Because that's the whole point of trying to avoid that split brain. If I have 2 leaders, then I have split brain because I've got 2 different decision makers. And we know that doesn't work. The leader has to have a quorum. In a new term, a candidate becomes the leader based on achieving that quorum. That's what distinguishes a candidate from a leader. Once the candidate has enough votes, they become the leader. Rule 2, you have to block the old leaders. You know, maybe the old leader was partitioned off from the network just long enough to lose its quorum, but still thinks it's the leader. Well, I'm the leader. That's why we use the term number, because if you say, I'm the leader of this term, and I look and I go, but I'm on term +3 of that, you're going to say, I'm sorry. It was nice knowing you, but you're too old now and I'm not paying any attention to you. Gosh, it's like real life. It is actually possible to have the same term number, but a longer log. That's like something went wrong and then we got back fast enough and the log grew. And that's how, if you're a replica, you know that, oh, there's some extra log stuff I probably need to pull over from the leader. And it will actually do this. The Raft protocol will actually get those missing records sent over. If you're the losing candidate, though, you're just a follower now. Sorry, better luck next time. And you step back and you just continue to play that follower role. If you don't have a winner, maybe because there's a network partition or you're in the minority partition of that, then no leader and you try the election again. So you will literally sit there and spin, sorry. And then what will happen is that somebody in the actual ops center will notice that the tail latency rates are spiking rapidly, or you go to down detector and down detector tells you that whatever service it is that you're trying to hit isn't working right now. Probably because something is partitioned in the network and we can't find the leader. Rule 3, so that was rule 3, try again. And then we randomize the timeouts to minimize the split vote risk, because we don't want to all send our proposal as a candidate at exactly the same time, because it risks each of us getting some small number of votes and not a quorum. In Raft, this is all about log replication. So each log entry contains the operation and the term number. So remember, we're replicating this log. That was the whole point of the Raft protocol. The leader will ordinarily have the longest of the logs because it knows more about the state of the system than any of the followers. But the followers, so like in our example here, one of those followers is actually current with the leader's log. The others are behind. And they'll catch up because of the way the protocol actually works. So in the first step, the leader actually pushes a new log entry plus the previous entry to the followers. If the follower has the previous log entry, they act that to the leader. In other words, I'm saying, okay, this is what I did last and this is what I'm doing now. And so I can tell as the recipient of this, oh, do I know about what he said was last? Because if I don't know what he said was last, then I don't have a current copy of the log. So my log is out of date. This is how we get quorum. That's kind of interesting, isn't it? So we get quorum by making sure the logs are all up to a certain point. But the log could actually be beyond that point. So the leader could be trying to get things to happen that we haven't received enough votes for yet. Once it has quorum, yes? It only acknowledges if it has the previous log entry. If it doesn't, then it drops it. And we're gonna get there. In fact, it's actually the note at the bottom, which says, yeah, we use this heartbeat thing that we're going to add as well, because that says, hey, leader, what's the current value? What's the current entry in the log? And the leader says, it's this. And you go, oh. And so now, remember in the primary backup, we had primary pushing to the backup. This is kind of like a pull model instead, where we're going to have the backup go to the primary and say, can you give me the entry after this? Or can you give me the entries after this, which would be a logical way of implementing it? So in fact, the question you asked was the next point on the slide. Perfect. That means they're in exactly the right sequence. So here we have a very simple example. Leader, 2 followers, that's our 3, so we can handle 1 failure. We have a client, and this is just the normal flow. So in the normal flow of things, the client asks us to perform a particular change. The leader talks to the followers. Once it has acknowledgement from one of those followers, it can ack it back to the client, and then we can let the other one catch up. So this is where we do see a little bit of that tipping towards liveness. We don't wait for everybody, which is what we did in like chain replication and crack and whatnot. Instead, now what we're doing is we're waiting until we have enough to know that that has been recorded, even though it's not recorded by every node yet. So the client's going to get an answer back a little bit faster. Logs are append only. When I'm trying to match logs, since they're all sequential and we've linearized our operations is what we've done. Once we see that 2 different logs have the same index and term in them, we know that they are up to date to at least that point. Remember what I said is that the leader sends the new proposed entry plus the last entry, and that means that the recipient, the follower, will know if it has the current log and is just going to append this next entry. So in essence, the new proposal becomes the commit of the old operation. Because now I can reason about that. I can say, oh, I got everything up to this point. I know that that is linearized on the leader, and therefore I can reason about the fact that I have everything up to this point in my log as well. It is possible to have an inconsistency here because we might have elected a new leader who hasn't received all of the log entries yet. Because remember, now we're kind of delaying, and it's possible for one of the followers to be behind. So the followers have to actually use the new leader's log. But our actual election protocol is what protects us here. The actual election protocol makes sure that even if the old leader had uncommitted entries in their log, the new leader has all of the committed entries in their log. So we literally do not have actually guaranteed the same log, depending on how we implement it. But we don't necessarily, there could be entries that we put into the log that never got committed. Gosh, this is an awful lot like Paxos. Except in Paxos, we use the term ledger. And in the part-time parliament, he's talking about writing things in the front of the ledger, those are your decisions, and he's talking about things that you proposed in the back of the ledger, those are your notes. I proposed this thing. Here, we've come up with a different way of putting all this stuff in the same ledger, but instead of Lamport's model of thinking of the front and back of the ledger, these are interleaved, and we are logically thinking about what's in the front and logically what's in the back. And this gives us a way of essentially saying, well, you know, that note I made in the back here, I'm not going to make a new copy here. I'm just going to be able to reason about the fact that, oh, yeah, I saw the next proposal, and therefore I know the previous one is hardened. I still like view stamp replication. I think it's much more understandable than this. The new leader can subsequently complete the commit process of previous uncommitted operations, but it only does that after it has committed at least one log entry from the current term. So in other words, somebody out there, like the old leader, knows about things that had been proposed. The new leader can now pick up those proposals and can put them out for vote and get them agreed upon and then commit them. That, I remember going through this and thinking, that sounds kind of complicated. And I'm pretty sure it is. Or you could just simply ignore them. That's probably what I would do initially. I would say, it's pretty complicated. I'm going to ignore it for the moment. Since we have these logs and we have these entries, and these logs could potentially grow unbounded because we could have lots of operations, we have a garbage collection problem. Lamport doesn't really talk too much about how many pages are in his ledger, right? But as you continue to fill the ledger up, you are definitely going to run into a situation where there's stuff in here that includes state changes that I don't need anymore. How do we get rid of it? How do we garbage collect this? If you remember when I talked about Corfu, Corfu was a replicated log that uses Paxos, by the way. It had a garbage collection problem as well, and it used a sparse mapping model. So basically, it could put holes into its log. So it directly tried to deal with exactly this problem as well. Roughly the same time frame, too. So the Corfu distributed log and Raft are very similar time frame pieces of work, about 10 years ago now. So how do we do garbage collection? We do snapshotting and log truncation. And this is always the problem when you start using logs, where you put things in there that you don't need anymore. You end up building a garbage collector. And as someone I know likes to say, the idea of doing garbage collection on disk drives was so bad that we decided we would call it something better. We call it cleaning. Because cleaning sounded more polite than the idea that you were going to actually like read and write lots of stuff on a disk drive in order to decrease the space you were using. Because has anybody taken compilers? Actually, any languages, like you look at garbage collected languages in general. Garbage collectors are surprisingly complicated beasts to build, and they're important, but we're doing it in memory, and it's slow. Imagine doing it on disk. Right. So that's why this is very important, and why optimizing this is often a significant part of the implementation. You don't have to worry about this. Everything we're doing in projects 4 and 5 is going to be in memory. So we're not really going to have to worry about slow compaction algorithms and dealing with that, the problems of real storage underneath it. But this is a big complication. The point, however, is we can reason about what can be deleted. We can reason about what we no longer need. Because if we have a piece of state that has been overwritten by some future piece of state, then we don't need it in the log anymore. Once everybody's at a consistent point, the stuff before that we don't actually need. The leader is complete. That is a property of Raft. So the log entries are not overwritten after commit. They are durable. The state machine that we're replicating is safe because we never overwrite the log entries for any node. But this is sufficiently complicated that if you want to know exactly why they have this argument for safety, you need to read the paper. I didn't go and read this part of the paper. I was perfectly willing to say, okay, I'll accept that for now. There's a couple of really cool visualizations of this. Let's see if I can actually click on it. I think this is the one that I liked. Of course, it will put that on the other. a node in your database that stores a single value. See, that's the extreme example I was talking about, where you have a Paxos implementation or Raft implementation for every single value in your database. That would be pretty extreme. And then we have a client, blah, blah, blah. So this is actually kind of a cool illustration of walking you through what Raft is actually doing, distributed consensus, the whole problem we've been talking about all term. Nodes are in follower, candidate, leader. Went through that. If they don't hear from a leader, then they propose themselves, see if they get votes, and then the candidate with the leader, enough votes, becomes the leader. That's leader election, blah, blah, blah. So now we add entries to the log. So the important point here is that we're adding entries into the log, but we're not committing the change to the database. We don't actually commit the change to the database until such time as we have our quorum. We get the votes, now we update the database. Now see, remember this was a database with exactly one value to make it super easy to illustrate. So we tell everybody what happened, what was the outcome of that. So we have a consensus, log replication, leader election. So this is actually kind of cool because they have different times that they wait for timing out on the current leader. And I have to keep clicking. The election timeout. There we go. This is the one I was thinking it was. Yep. So you'll notice that they time out different values so that the follower with the lowest timeout will be the one that says, will probably be the one who wins. And so it's just walking through the election protocol. And then there's these periodic messages that go back and forth, the heartbeat, I mentioned briefly before. And so the leader is basically telling its followers, I'm alive. And it's going to sit there and keep saying, I'm alive until it stops, in which case then we're going to go through a new election policy. That's actually going to depend on your implementation. I don't believe that they specify it has to be done in a particular way. I mean, if you think about it, you ideally want to have them choose a different value. But if you've got 150 millisecond range and you just simply chose a random value in there, that's probably still enough scatter. But you might take the IP address and do some mathematical hash and then mod 150 and add it to 150 kind of thing. And then you have a deterministic timeout, which would tend to give preference to one of the candidates. So you could do it either way. So here we go. Watch the election. There we go. All right. And it literally makes us sit here and watch the timeout values and whatnot. So node B is now the new leader. Node C is currently the one that we think is dead. Since we require a majority, we can only have one leader per term. It is possible for us to have a disagreement where we have two nodes that think that they are the leader. But in that case, then neither of them will actually get a vote. Now see, this is the case of 4 nodes, which is just a bad idea because we can get these kinds of split elections. So if you like these kinds of graphical animations, it's good to spend a little time walking through this and see what I'm rambling about here. since we didn't get a majority, we have to do the random timeout thing again. And that might be a reason to randomize it each time. So you don't end up in some weird state where you have two nodes that have exactly the same timeout value. And if you have a source of real random noise, that would probably be ideal. And this is enough of a problem that modern systems actually have sources of like random entropy that they can use for generating random values. Because when these get synchronized up, it's really easy when we're using something like the framework to rely on the fact that it is deterministic. In other words, we choose the same seed value for our pseudo-random number generator, and we're going to get the same sequence of events. So that's one of them. I'm going to put the other one in as well. It show up now. Slide. Now I clicked on it. There we go. That's what. This is a different visualization as well. So I put these in here because I think they actually are helpful in better understanding why people like Raft. And this one's fun because you have little sliders so you can change the timers and the sensitivity of things, and it shows you the database as it mutates over time. So both of those can be useful in trying to better understand how the Raft protocol works. So what do we talk about? I spent a decent amount of time talking about Paxos, and part of the reason I did that was because it's been a while since we talked about Paxos. We went from Paxos to, which is kind of really complicated, to ViewStamp replication, which seemed to flow really well. I really liked the way that it flowed through things. And now we're on this other protocol. And as I said at the beginning, part of what's interesting here is they're ultimately very similar protocols. There are very small differences between Paxos, Raft, and ViewStamp replication. They're all based on the same fundamental idea of quorum consensus. And the difference is mostly about how we pick a leader. Once we have that leader, the protocols once again look very similar. Raft focuses very specifically on a replicated log model. When you look at ViewStamp replication, it isn't focused on a replicated log model, it's focused on a replicated database. But you achieve a replicated database with a replicated log. So there's a lot of similarity there. And the actual details of the protocols, when you stand them up side by side, you go, wow, there's an awful lot that's the same between these. And I hadn't really picked up on that with Paxos until somebody was asking the terminology questions, and I start standing these papers up next to each other and literally going through them and saying, yeah, when you actually look at them, it's really hard to tell them apart. That it's deceptive because the terminology that they use is different, but the problem they are trying to solve is the same, and the approach they use to it is very, very similar. Which one should you use? It's good to know them all, because what you're going to find is that in different situations, you're going to want to use different protocols. If you have a problem where a replicated log solution is really what you need, then using Raft probably makes the most sense. If you are familiar with Raft and not familiar with Paxos or ViewStamp replication, using Raft probably makes the most sense. If, on the other hand, you are familiar with Paxos and not so much with Raft, you're probably going to stick with that. So what you know may very well be what you stick with. Actually, it was a result of going through all of this and me thinking about this and saying, these are really, really similar, that ultimately prompted me to, it wasn't in the original syllabus, I added it. So what I'm going to talk about on Thursday is formal verification. Now, I'm not going to dive deep into formal verification. What it's mostly going to be do is to talk about what these are. And it's all about building models. And the reason this reminded me of that was because these models are exactly what we're talking about. Each of these has the same basic model, but achieves their goals slightly differently. One of the hardest things about getting these systems correct, and the reason you have proofs in these papers, is because what matters is what guarantees can we actually provide. Formal verification gives us the tools necessary to provide descriptions of our models using formal language and to utilize actual techniques for proving that our models are correct. Does that mean our implementation is correct? No. No. Ivan has a whole set of work in this space where they actually try to take formal models in TLA plus, which is the big tool I'll be talking about on Thursday, and generating code, Go code, directly from the model. And the problem is that the implementations end up being very slow, and so part of the challenge is how do you make them faster. But having a working model is what I suggest, whether you do it formally or informally. You have to have a working model as you're working on Project 4. Because if you don't have a working model in your head, it's never going to come out in that code. Because the reverse isn't guaranteed. If you do have a working model in your head, it may not come out in your code anyway. But I guarantee you, there's no chance, if you don't have a working model up here, you're going to have a working model when you're sitting there at the keyboard. And look, I managed to finish on time. 2 lectures in a row. Gary, any questions? We'll see if I can do that on Thursday. There's a lot of material on Thursday, but a lot of it is really, again, pointing you to things that you can look at if you find yourself in a position where you're really working with distributed systems and really trying to use these protocols. These are tools that will be worth learning because they really use them. It's amazing when you start looking at TLA plus and you find out that all of the cloud vendors have started using formal verification techniques for at least pieces of what they've done. All right, well, I wonder if I'll have more than 7 people on Thursday. That's it. See you on Thursday, assuming that there's no more snow and whatnot.